Welcome to this session of COMSOL Tips and Tricks presented by Altasim Technologies. The title of this session is Resolving Wavelengths. The example problem that I will use to demonstrate this tip is that of a time harmonic pulsating sphere. This is a pressure acoustics problem solved in the frequency domain. The small solid sphere in the center pulses at a velocity of 1 meter per second at a frequency of 250 kilohertz. The spherical wave pattern that results in the air domain surrounding the sphere is shown in the image. This example was chosen to highlight the importance of efficient meshing in order to accurately resolve wavelengths. Simulation engineers know that the finer the mesh, the more accurate your results. However, we never want to go overboard with mesh refinement, because as we refine the mesh, we are increasing the time and computer memory required to solve. This is a classic trade-off issue that motivates the need for strategic and efficient meshing techniques for engineering simulation. In the context of wave-type problems, efficient meshing means accurately resolving the smallest wavelength of your system without going overboard. Having around 10 to 12 degrees of freedom per wavelength is recommended for accuracy. Going beyond this is too much and can be a waste of resources. Assuming you are using linear element discretization, you will want about 10 to 12 elements per wavelength for accuracy. Using quadratic elements, which have an extra mid-side degree of freedom per element, will only require 5 to 6 elements per wavelength. COMSOL's free meshing operations will automatically create the coarsest mesh possible within the constraints you provide in the settings window. For example, you can set the maximum element size to not exceed a certain length. Being strategic with this setting is a great way to generate an efficient mesh. Also remember that in COMSOL, anywhere a value can be entered, you can also enter a parameter. To make your model even more elegant, define your minimum wavelength as a parameter. Then under your mesh settings, specify a maximum element size based on this parameter. Taking a cut line of data as shown in yellow, we plot the spherical wave pattern for different mesh resolutions against the analytical solution from the literature, which is shown in black. Solving problems for which there is a known analytical solution is a good way of validating your modeling technique and mesh resolution selection. As we increase the number of degrees of freedom per wavelength from 3 in blue to 12 in magenta, the COMSOL simulation results converge upon the analytical solution nicely. Next, I will take a few moments and show an overview of how this model was set up in COMSOL. Okay, the first thing that I would like to show is the parameters list. Here's our list of parameters for this model. You can see there's a parameter u_0 to find the velocity of the pulsating sphere at 1 meters per second. We have our radius of the solid object in the center here, A, at 2 millimeters. Then we have our density and speed of sound in our fluid. So these represent the density and speed of sound in air. F_0 is the frequency of the pulsating sphere. Right now set to 250 kilohertz. But again, these are all parameters, so these are easily changed. And then we have these two parameters, which are going to be important when we go to our mesh settings. Lam is the wavelength of our problem, which is the speed of sound divided by the frequency. And then DOF_per_WL, degree of freedom per wavelength, is where we specify how many degrees of freedom we want per wavelength. And we're going to use these two parameters, Lam and degrees of freedom per wavelength, to parameterize our mesh settings, which I'll show in a moment. But to move on to the physics setup, that's accomplished here on this pressure acoustics frequency domain node. And if you expand that, you can see our model builder tree. And as you can see in the graphics window, the problem is solved in the 2D axisymmetric space dimension, where the blue domain is revolved 360 degrees around the r=0 axis here, this dotted red line. Additionally, we take advantage of the half symmetry plane that slices the sphere in half here. On this head physics node, if you go down here to the bottom under discretization in the settings window, you can see the element order. This is where we've selected linear for the element order. By default, COMSOL usually has quadratic as the element order. With these quadratic elements, there's an extra degree of freedom per element placed at the mid side of the elements. But for this problem, we've selected linear for the element order. On this pressure acoustics model node, in the settings window here, we can see the equations that we're solving for. And here's where we specify the speed of sound and density of our fluid using the parameters we defined under global definitions parameters. We can also see that this node here defines the axial symmetry condition along the red dotted line here. We can also see that there's the symmetry condition along the bottom here. And then there's a normal acceleration condition applied to the boundary where the solid touches the fluid. And this is what's going to simulate the pulsing of the solid body. And then on this boundary, we've specified what's called a spherical wave radiation condition, which allows the waves to propagate out into free space. So that's the physics setup. Moving on to the meshing setup, we can see that we have a free triangular operation specified for the fluid domain. And then we have this what's called a local size node, which is a subnode that governs the behavior of this free triangular operation. And in the settings window, you can see that we've selected custom for the element size. And then we're able to go under element size parameters and check this box maximum element size. And then we've changed off of the default and entered in this expression lam divided by degrees of freedom per wavelength. And this ensures that the free meshing operation will not build any elements larger than the wavelength divided by however many degrees of freedom we want per that wavelength. If you were using quadratic element discretization, you would want to divide this expression by a factor of 2 because of the extra mid-side node present for quadratic elements. So in that case, I would just simply divide this expression by 2 if I had quadratic elements. And that's going to give me an efficient meshing for this problem. Now moving on to the solver setup. That's accomplished under this study node. And as you can see, we've added a parametric sweep. So actually what we're going to do is solve sweeping across this parameter degrees of freedom per wavelength from a value starting at 1 in increments of 0.5 up to 12, which is our max degrees of freedom per wavelength. So what this solution process is going to do is incrementally increase the mesh resolution, and we're going to be able to show how we have converged in terms of arriving at a converged mesh for this problem using this parametric sweep. So the solution is already stored, and if we go to this 3D plot group, we can see that the final parameter value of 12 degrees of freedom per wavelength is the one that's visualized here in the graphics window. We could decrease that to say 2 degrees of freedom per wavelength and then click plot and see that the solution isn't very good. We could also increase that a little bit, let's say 5, and see that the solution is getting a little bit better. We could zoom in here and see that what we are plotting here is indeed about 5 degrees of freedom per wavelength, about 5 linear elements per wavelength. If counting from this point right here on the peak in red, number of elements to the next peak, 1, 2, 3, 4, 5, just about 5 elements per wavelength for this particular problem. And if we increase that up to 12 degrees of freedom per wavelength and click plot, we can see the solution changes a slight bit, and this is our converged mesh. We can animate these results not in time, but animate across the mesh resolution space. And you can see how, as the mesh is refined, that the solution converges Here's our 1D plot group that we showed in the PowerPoint slides earlier, and you can see as we get closer to 12 degrees of freedom per wavelength, which is the recommended value for accuracy and not overmeshing, that the magenta curve falls pretty nicely along this black curve. Thank you for taking the time to watch this installment of COMSOL Tips and Tricks presented by Altasim Technologies. Please visit our website for more video content or for information on our popular training courses and other services.